So I can wish everyone officially Happy Garbage Day.
Woo.
Thanks for coming back on this glorious Tuesday. Let's see, 49 feels like about 12 outside, something like that. Yeah, welcome to April. We're not fooling. It's still freaking winter. Hooray. So no April Fool's jokes today. Apparently other folks are having fun with that, but I hesitate to do anything that could be perceived as mean. My son's preschool teacher, I think kindergarten, had a really fun thing that they did. They told the kids that they were going to get brownies, and what they made was construction paper brown letter E's, like brown E's. But they had baked brownies too, so they still got their brownies. But then he used that brown E as a bookmark, like for the rest of the year. And every time I saw that, I thought, this is cute. And apparently Ariel did that today, I hear too, that he had the same prank, and that's what Erica said. So he had the same independent idea. So yeah, I thought that was amusing. Some other good news that I wanted to share, both on the recording, Vladimir is now an award-winning teaching assistant, according to the University of Iowa. Please congratulate him. Yes, so we nominated him for his work during the last calendar year, and he was chosen as one of the recipients. So very few folks across the university get that award. You should feel very proud. And we're grateful to have you in this role. So thank you for your work.
Yeah, thank you.
Yes.
Good job.
Great recognition. Wonderful. Yes. Other news, let's see. The Zoomers are congratulating you as well. So confetti and whatnot happening on the screen, as you can probably see. Let's see. I spent the mornings reading through your outlines. I'm about halfway done. So I'm trying to get them back to you hopefully tomorrow. The way that they will be delivered is through the online homework portal. So that's why I had you name your files in a particular way, because the software that I wrote creates a dynamic link so that you can download your document. I can put together the link based on your name in the database. So that's why. Let's see. For folks that I'm asking for additional information, the reason I'm trying to get these back to you as quickly as possible is because I'd like to have revisions back next week. So if I need to answer, I need some more information from you, or in some cases, folks propose to do too much, and I'm like, you got to pick something narrower. What are you going to land on? A few folks are still waiting on collecting data. So I think by next week, you got to have your data in hand. Otherwise, this is not going to go well. I really don't want to put folks in the position of like waiting on data and then having to wait till the last minute because of that sort of structural issue. So if you're someone who's in that position, I could potentially help suggest things. The homework plan document had a list of various places to go to look for data. I also wanted to apologize because I realized what had happened. I had saved a new version of it like in the wrong place and then overwrote it with the previous one. And so that's why it says homework 5 on everything instead of homework 4, because last year it was homework 5. So I apologize for the confusion on that. What you are working on is a plan for homework 4 that will become, the document for that is there. And then the rubric for it, the instructions are right here. So it is 4, not 5. I'm very sorry. And I'm actually fixing your individual plans to put it 4 everywhere instead of 5, and so that you're not confused when you get your plan back. So I'm imperfect. I'm sorry. Stuff happens, particularly when you're trying to do things quickly to get stuff off your list. You know, more imperfection happens that way when we're rushing through things. Am I right?
Mm-hmm.
Yep. And just as a reminder when you're working on these things, so homework 4, your first draft is due April 28th. So you've got a couple weeks. It does not have to be complete. It does not have to be perfect. It needs to be 3/4 complete with respect to points attempted. And I can help you get the remaining pieces. So if you run into trouble, you can't get your plot to work, you know, something breaks, you're not sure what to do, like you can write questions and comments and we can have a dialogue about that. But I just need to have enough material to give you feedback in the first place. I hope to have your feedback to you within a week or so because revisions will be due on the Thursday of finals week. And note that they are optional. Okay, so if you get your points back and you're like, I got 14 out of 16, I got other stuff to do, I don't want to revise it, fine. Fine, I'm fine with that. I'm a very pragmatic person. But if you're like, I'm going to revise to get my 1/4 point off that you took back, you can do that too. It's fine. There's all different room for all different kinds of personalities and approaches to grades and whatnot. And I don't know what your priorities are, but I trust you to establish them as knowledgeably as you can. So I am working on that. I will let you know when your feedback is available for that as well. Any questions on that much? Okay, so then the next thing we're working on is homework 3. That is due next Monday. That's on counts and fun with interaction terms as one of the main things. Like, no, it's not fun. No,
It was a challenge.
it was a challenge. Good. You're welcome. I maintain that if you could learn this stuff from Google University in 10 minutes on your own, you'd be wasting your time and tuition dollars. That's what I will maintain. For those of you who haven't opened it yet, I'll give you a brief overview of what Homework 3 is about. It's based on a true story, like all of my homeworks are. It is the story of food school. So my son, who is currently 10, is the world's pickiest eater. He'll eat like 5 things, and he's trying to voluntarily die of malnutrition if we let him. Like if I left him alone all day, like he wouldn't eat. Like he just wouldn't seek out food. You know, some kids like they constantly want to snack and stuff. He's the opposite. He never understands when he's hungry. But this has been a lifelong thing, and I was concerned about him actually getting malnourished when he was younger. And his pediatrician suggested this program that we were in for about 10 minutes because then the pandemic happened and we couldn't finish it. And we called it Food School. And it was a program where occupational therapists were working with him to try to get him to like, can you touch the food? Like, can you just have it like in front of you? Like, can you smell it? You know, can you lick it? Like, and it's just like working our way up to eating things and making it sort of like less stressful and all of that stuff. So it turned out that part of what they wanted us to do as parents was to provide a buffet of things for them to try at most meals. And I don't know about you, but I'm certainly not going to spend 2 hours preparing a buffet of food for my child to reject every single one of it that isn't mac and cheese. So the program from the home perspective sort of started to fall apart pretty quickly. And thus the genesis of the homework problem. What is the differential effect of food school training on people whose parents work full-time or don't? So that's the background of the story. All my homeworks are based on true stories, and most of them are based on like preschool because that's when I originally was making up these homework assignments. So I will continue to ask if you have questions on that. You can also send questions to either of us on email. Of course, we've got office hours as usual this week, next week, etc. So no questions right now on that, homework 3, next week? No? Okay. Let us know if you need anything. Yeah, after that, homework plan revisions. I'll let you know when we've got a formative assessment, one more bridge activity, then homework 4, and we're getting there. We're getting there. Got some new stuff to talk about today. It is lecture 4 and example 4A, so if you haven't grabbed that already, please do so. It is a catch-all, models for other not normal outcomes. So like the potpourri or miscellaneous section of the program here. Not that one yet. There we go. So lecture 4. Anything that I'm forgetting to mention before we dive back into stuff? Can you think of anything? Nope. Okay. Well, let me know if you do. And Zoomers, I'm assuming you can still hear me and see me okay? Yep. Okay. Excellent. Thank you for the feedback. All right. So where have we been? Where are we going? So generalized. When you hear that word, what should you think? Not normal. Exactly. So general linear models is actually not very general, contrary to the term. The word general means something very specific, that you're saying your residuals follow a normal distribution. Your normals follow a residual distribution, actually. That's what I was going to say. I'm on water, too. Your residuals follow a normal distribution. That's what a general linear model says. So what if they don't? Well, it turns out there's a model for that. So as it turns out, the 3 assumptions that you're taught in standard linear regression, residuals are supposed to be normal, they're supposed to have constant variance, and they're supposed to be independent. All of those things are solvable by changing to a different kind of model. So there's never a point at which you're like, oh, I can't do an analysis, it doesn't meet the assumptions. It's like, okay, find a new model that has more reasonable assumptions. So the ones that we've talked about thus far are sort of the textbook examples of when a general model would not be appropriate. So categorical data is a big one. If you don't even have numbers in the first place, there's no way those residuals are going to be normal. We did that for binary, we did that for ordinal, we did that for nominal. What's the difference between ordinal and nominal? The link, yes. So it's a cumulative link for ordinal, like 0 versus 1, 2, 3, 0, 1 versus 2, 3, 0, 1, 2 versus 3. What is it for nominal instead? What kind of link function would be used for a nominal response? You can describe it or come up with the name, your choice. Zoomers can play too, I'm watching the chat. I'll give you a hint. I describe it as like dummy coding for your outcome.
Isn't we have like a reference category and
Yep.
then
Yep,
how you and then you do subtractions to get actual difference between them if you choose.
yes, so it's called either baseline category logit. It's also sometimes called generalized logit, which is really unhelpful because that's the entire freaking class. Baseline category logit means you designate one answer choice as the reference, and then you have the logit or probative answering each other one relative to that reference. So it's not cumulative. Each submodel only has the two choices that you're focusing on. So that's what differentiates ordinal and nominal responses, is the kind of link function that's used to create the binary submodels. Either way, though, if I have 4 outcomes, I need 3 submodels to do that. 4 choices, 3 submodels. And multinomial is the response distribution regardless of what your link is. That just means more than 2 categories. It's a discrete distribution for categorical data. Then we did counts. We just finished counts, right? What kind of link do we do for counts? Log. Do you want to sing? Anyone? No? It's log. It's log. Yes, log link. And that's pretty much the only one that we see for counts. There's a few others that I've heard of, but I've never actually seen them, and they're confusing, so I'm not going to do it. And then I have some kind of Poisson or negative binomial. What's the difference between these two? Yes, indeed. Poisson says mean and variance are the same number. And negative binomial says actually the variance needs to exceed the mean by a quadratic function of the mean with the stretchy factor, so a multiplier. So that is used when we have a lot of positive skewness potentially, or just a lot of extra variability for higher counts. So that's a pretty common way to solve that. What does zero inflated mean? More zeros than the distribution thought it should have. That's what it means. So like a count distribution for Poisson expects some zeros. The question is how many does it expect, and are there more? There's 2 ways that we saw on, I think it was last Thursday, to deal with this. And these involve submodels as well. Guess what? Those same principles we're going to do in this unit as well, which is why I'm reviewing them. It's the same. So zero inflated models say, okay, what is the count predicted to be, including the zeros? And then what is the logit of the probability of being an extra zero? Like you predict the inflation aspect. And that gets to be conceptually confusing because you don't know which kind of zero a given person is. You don't know whether they're in the inflation distribution or the regular distribution. The alternative is a hurdle. How do we do that one? If and how much? Yeah, we cut off the zeros. So then we have submodels that say, are you a zero or not? That's a logit. And then if you're not a zero, how much are you? Then you predict the amount. So it'd be like, are you a smoker or a non-smoker? If you're a smoker, how bad of a smoker are you? That kind of thing. Do you have a history of adverse childhood experiences, yes or no? If yes, how severe were they? So there's a lot of phenomena where the difference between 0 and 1 is a big deal, and it's a different qualitatively thing than differences among the amount parts. And so the if and how much, if the how much part is a count, you could do that with some kind of Poisson or negative binomial. If the amount part is continuous, that's where we're headed in this unit here. So we're talking about continuous stuff, potentially with boundaries or not, proportions, other kinds of truncated stuff, and skewed continuous. So catch-all stuff for the rest of the kinds of distributions. And these ones tend to be Like, it's less clear what the right answer is. Like, there's multiple reasonable things that one could do. So that's reality. So that's why I'm putting it together. Is that funny?
I think it's great because I'm like, I'm like, okay, for what I'm looking at, I'm pulling together proportions and truncated. So I have truncated proportions.
Yeah.
Yay.
Yeah, it's a great time. We're going to have a good time with this. So for those of you who are working with like accuracy as an outcome or proportion anything, this unit's for you. So beyond categories and counts, those are the obvious cases in which one would turn to some kind of generalized linear model, but there's others. So if we think about what the normal distribution entails, it's supposed to be symmetric to begin with. It's supposed to be truly continuous and unbounded. I can't for the life of me think of an outcome that really is normally distributed, like that is truly continuous with no boundaries. Like in practice, measurement has boundaries. Like if you give someone a test, someone can get them all right, someone can get them all wrong. If you measure response time, the fastest you can be is some sort of like biological limit of like, 200 milliseconds or something. But yeah, like it's truncated essentially at 0. Question?
Income and debt.
Uh-huh.
How much do you make? How much do you owe? Who would be closer to?
Yeah, so net worth conceivably could be continuous in terms of going into the negative territory or the positive territory, unfortunately. But income, per se, is bounded at 0. I think the same thing could be true of house prices. Like if you buy a house, you have at least a little bit of equity in the house. But if you need money, you can take the equity out of the house and borrow against it. So you could actually end up owing more money than your house is worth because you borrowed against it. So your home value, like net, could be negative. Like you got to pay to get out of it. 2008 called. Hi. The last housing crisis, people were doing that in the United States. Not a good time. Hopefully not going to do that again. So in terms of other kinds of outcomes that we would want to consider generalized models for, continue-ish is the word that I made up for this. This is not a real word. This is my word. So don't write that in a manuscript, okay? It's not going to go well. I make up a lot of words when I teach this stuff that I would not put in a manuscript because this is like classroom Lisa versus writing Lisa versus presentation Lisa. Like when I give presentations at conferences, I don't even swear.
That's boring.
I know.
Well, why the F not?
Exactly. Exactly. I did make one joke one time that the acronym DDFM and SAS PROCMIC stands for dude, doesn't freaking matter. And that got a big laugh. But that's the best I've done. I try not to swear in workshops either because you never know who's in your audience. But sometimes when I'm just sitting up here having fun with y'all, I just, kind of let loose. But continue-ish is an example of that. It's not profane, but it's not a word. What I mean by this is things that are not really continuous, but it's reasonable to pretend they are. So things that would fall into that category, proportions and rates, like accuracy or percent correct. How much of the time were you on task? Those kinds of outcomes. Scale scores. So if you have the sum of 5 items, for instance, a lot of you have that kind of data that you'll be looking at in your project. Most people would say, oh, that's continuous enough, it's fine. But no, I mean, if someone picks the lowest answer category for every question, there's going to be a floor effect. And the same thing will happen if someone picks the highest answer for every question. And you could have some of both. So if you have a question, like a set of questions that's really polarizing, where you might have people that a lot of people would disagree and a lot of people would agree, you can end up with something that's bimodal. So there are distributions actually that could work for that as well. But most of the time it seems like it's skewed one way or the other. Question? Or no? Hair maintenance. Gotcha. Okay. Here we go. So logit links can be used to solve 2 boundary problems that would be found in here. So what's the smallest a proportion can be? 0. What's the highest a proportion can be? It's 1.
It's not.
Yeah, so proportions are bounded between 0 and 1. Does that sound familiar? Like zeros and ones? How'd we fix that before? Logit. Hang on. The log of the odds of the probability of a 1. Yep, that's how we're going to fix it here too. The only difference is that in terms of what the y could be, it's not just zeros and ones. It's anywhere between 0 and 1, too. So it's continuous but bounded. So we're going to need to figure out what kind of distribution will work for that, and the answer is going to be something in the binomial family, most likely. We also have continuous outcomes that are bounded in only one direction, analogous to counts. So response time, salaries, costs of anything, minutes of physical activity. What's the fewest minutes of activity one can have in a day? 0. Yeah, at my house we call that Saturday. Like I'm just toast. I'm on the couch on Saturday, not doing much. Maybe
or continual, depending how you define activity.
it's true. Like usually it's like minutes of vigorous physical, like that's how they say it. You know, it's like, nah. My watch is like, did you take a nap? Like, or have you just not moved for 2 hours? You know, that's when you know you've hit peak Saturdays, when your watch thinks you were asleep for some part of the day where you weren't. You were just that inactive. Good time. So in this case, we don't need a logit, right? Because we have positive end can go as high as it wants to go. Like, what's the most expensive house you can buy? I think the first time that I taught this class, I had seen a newspaper article like 175 million was like set a new record for house prices in California or something. Yeah, unbounded. We can do a log link. So log links keep things above 0. The only question then is what kind of distribution will we need? Because if it's continuous, then the Poisson family, negative binomial, is not going to work. It's discrete. So logit is back. Too logit to quit. So we're going to predict proportions, but in a roundabout sort of way. So I want to try to describe this in as few confusing words as possible, but I know it's going to be confusing at first from previous experience. What we're doing at the end of this is predicting accuracy, like predicting the proportion. Okay, that's where we're going to end up in a very roundabout sort of way. So proportions range between 0 and 1. So the model needs to understand that it can't predict below 0 or above 1. Okay. What we're predicting is P, the probability of a 1 for any trial. And this is the binomial language that we use. So if I give you a test with 100 questions, that's 100 trials. The best you can do is 100%. The worst you can do is 0%. And for outcomes that are stored as accuracy or proportions already, that's what I would do. But you can have this for anything. Like if your test has 27 questions on it, then it's 27 trials. And it doesn't matter because what the model is focusing on is for any one of those trials, what is the probability of getting that correct or endorsing it, if you think of it as like symptomology or something like that. So we're back to predicting the log of the odds of the probability of a 1. We just have more than one shot at getting a 1. So then to get the predicted probability, once we have that, like let's say that my predicted probability of a 1 on any trial is 0.83, yay me. I would multiply that by the number of trials, and then that becomes my mean. So if I have 100 trials, then I would have an expected value of 83 out of 100. So there's that extra last step that puts it back into the original like event metric, but the model essentially is going to predict accuracy or the proportion directly. It's just this roundabout way of sort of doing it. So it's actually advantageous that it's set up this way, because then you can include people who have different numbers of possible trials. So what if you're observing children and you're tracking their disruptive behavior over a period of 2 hours? You could do that, right? What if some kid was so disruptive that they got pulled from the classroom and you couldn't watch them for 2 hours? Well, then their amount of disruptive behaviors needs to be like downweighted by the amount of time that you were able to observe them. So if you turn that into like rate of disruptive behaviors, you could tell them that this kid was watched for 2 hours, this kid was watched for 1 hour, and it will still build in the rate. So you don't have to have everybody following the exact same set of possibilities here. That's what's happening. So in terms of modeling these things, if you have an outcome that's not scaled from 0 to 1, but features the same kinds of distributions, like ceilings and floors, you can rescale it to go between 0 and 1 with this formula. So I'm assuming that's what you had done to turn yours into proportions? Maybe? Something along those lines.
All I did was a division, which is what you recommended.
Okay, so there's multiple
Yes.
ways to do
Yeah,
that,
yeah,
but this
yeah.
is one of them.
But yeah.
So from going from the data to the model, we're predicting mu here in logits, the log of the odds of the probability of a 1 for any one trial. And then to get back to data, it's e to the logit over 1 plus e to the logit. So it's the exact same thing we did for binary, ordinal, and nominal. Guess what? Effect sizes, odds ratios are back because we're in logits. Same thing. So e to the slope in logits is how we would get an odds ratio. The question then is, what would we do with respect to distribution? So we're going to use logits. Could use probits if you wanted to, but we don't need to do that. The question is binomial, beta, or some kind of hybrid. So I'll show you pictures of what these look like, but here's a comparison for you. Binomial is less flexible in that it only allows either a ceiling or a floor, but not both. But it's more flexible in that you can have perfect scores. So you can have a probability of like 0 events out of the number of trials, or you can have all the events out of the number of trials. Zeros and ones are part of a binomial distribution. Then there's beta. It's very, very flexible. Do not ask me to explain how it works. I can't. I never will. It doesn't make any sense to me. And the reason that it still doesn't is because I haven't had to use it because it doesn't actually include zeros and ones. So you can't include scores that are perfect, perfectly perfect or perfectly imperfect within beta. So that's a big limitation. However, some genius figured out if you take the best of both of these and create something called a beta binomial, then you can have over-dispersion that works pretty well for situations in which the variance exceeds the mean, just like in count data. So this is going to be the analog to negative binomial, essentially, in counts, called beta binomial. And here are the different packages in where you can find all of these various things. So here's some pictures. Here's the binomial distribution. You probably learned about this in intro stat with like drawing like colored balls out of an urn and like, and how long does it take before you get, you know, a red one or whatever? What's the probability of getting 2 balls of the same color? All that kind of stuff. You also might have seen this with a series of coin flips. Like how often would you get 4 heads out of 10 if it's a fair coin? That kind of stuff. Well, that same machinery can be used to predict outcomes that are bounded between 0 and 1. So I have the probability, for instance, that my outcome is any particular number of events, so you can think of this as the number of right answers out of n trials, is predicted with this formula, and the only parameter in this distribution is p. So it's just like Bernoulli in that sense. The way that it differs is that you multiply the probability of a 1 for any one trial times the number of trials to get to the mean. So if I have this blue distribution here, this is made from having a 10% chance of getting any event either correct or endorsed, getting a 1, whatever that happens to mean. And you get 20 tries to do it. This is the expected distribution over those 20 tries, if that's the mean. So note that it's creating a distribution that's a little bit skewed, and it understands that the lowest you can have is 0. It stays within the lower boundary. It does not expect very many cases to be over here. So like if the best you can do is 20, but you only have a 10% shot at any one trial, 20 is really, really unlikely. So the distribution you can't even see on this side. Green is the opposite. So this would introduce essentially predicting a ceiling effect. If the probability of getting a 1 on any of these trials is 0.9, then this would be the expected distribution over 20 trials. And then red looks kind of nice, doesn't it? It looks symmetric. It looks normal-ish. It's not continue-ish, but it could be. So for situations in which the mean is about 0.5, then a normal approximation to the binomial might not be that terrible, because it's at least the symmetric part, and then you may not be in a situation where you're worried about going outside the boundaries if they're far enough away from the rest of the data. So this is a natural way to accommodate outcomes that are skewed. However, we got to worry about over-dispersion. So more variability than the mean predicts. It's the same thing here. The mean is given by the number of trials times the probability of a 1. If I take off the n part and block it with my giant pink mouse, there. P times 1 minus p. That's what variance was in the Bernoulli as well. So variance is determined by the mean. The question is, what if you have extra variance relative to what's expected? then we got to worry about that. So over-dispersion is a problem in binomial data that we need to be concerned with. You already know how to do it. Guess what we're going to do? Yeah, feel free to read from screen. I spoil my own surprises.
Chi-square test.
Yeah, we just learned about this new Pearson chi-square over degree of freedom thing, where the numerator reflects basically what's happening in the data, the denominator reflects what's happening supposedly in the model, and the ratio is informative. So if it's above 1, that means you have too much variance in your data relative to what's built into the model, and your results are too optimistic. So we're going to solve that with the same diagnosis. We can do likelihood ratio tests to compare alternative versions if they're nested, so we'll do that as well. Over-dispersion can be caused by other things. So if there's stuff missing from your model, that can cause it as well. But if you add all the things that you can think of and it's still over-dispersed, then you would switch to a different distribution. There's 2 different ways that we're going to introduce over-dispersion, though. One is additive and one is multiplicative. And I will show you how to fit both of those. The question is whether you just want to add more variance or whether you want to tie it to the mean in the way that negative binomial is. The latter, multiplicative, works like that. So we will see those as well. Here's beta. Look at this monster. Thank you, Wikipedia. Beta can look like anything. My favorite is the orange one. Like, this is a beta distribution that it understands bimodal data. Then we get something that looks like blue here, would be like something that's positively skewed a little bit. Green, negatively skewed. Pink, reasonably symmetric. It can be anything. So beta ranges between 0 and 1. It does not include 0 or 1. So it's limited in practice. And there's various ways of parameterizing it. And alpha and beta are the things that go in here. And if they're both the same number, that's what made orange. If alpha is more than beta, that made green. Like, if alpha is less than beta, that made blue. That's the best I can do.
So if they're the same, it's symmetrical, because pink and orange are both alpha equals beta, alpha's 2, beta's 2.
Yeah, pink is symmetric, and it's 2 and 2. Orange is also symmetric, but it's less than 1, and I think that might be why it flips upside down. I think.
That makes sense.
And this is where if I had actual statistical training, I might understand better, but I don't.
But
Gamma
it's like
is a
for
strange
odds
one.
ratios, right? Because less than 1 is a fraction.
Yeah, less than 1 is a negative slope in odds ratios, yep. And positive slopes are above 1.
Yeah.
Yep. So this is where if you wanted to use this, you'd really have to do some deep digging in the documentation for your software and figure out how it's parameterized. But like in SAS, this is what they said. The mean is alpha over alpha plus beta. And what they're calling variance is a function of this scale thing, which is alpha plus beta. This makes 0 sense to me. So we're not going to do it. We're going to hack it. So if you wanted to use beta for data that had 0s and 1s, in addition to proportions in between, you'd actually have to add submodels to it. So if you had 0s, between 0s and 1s, you'd have 3 different submodels. You'd have the logit of the probability of a 0, the logit of the probability of a 1, or the logit of the probability in between. Anyone's head hurt thinking about that? Just me? 3 submodels for one thing? That's a little tricky. So no. The beta binomial distribution is the one that I think will end up working best for most purposes. It's a hybrid. It says that the binomial p parameter itself follows a beta distribution. So what this translates to in practice is a stretchy type of scale factor, just like a negative binomial. So it's a variance multiplier that allows the variance to exceed the mean. The only question is what you get back. So this scale factor goes with, what is this one? Help me out. Delta?
No, that's phi.
That's phi? Okay, yeah. I don't remember my Greek letters. Phi?
Delta is kind of the weird D.
Yeah, so
yeah.
phi or phi?
4. Oh.
Yeah, phi, phi, pho, phum, I don't know which one. But it's given just as this scale factor in SAS. It's 1 over that in Stata, and in R, it's the log of 1 over that. Because why not? So because of these differences, I have tried and to figure out exactly what the variance function would be, and I got close for some of them, but then I had to give up. So this is where it starts to be very tricky. But the thing to hang on to is that beta binomial has this additional piece that allows the variance to grow with the mean. And if it fits better according to a likelihood ratio test than standard binomial, that's what we should use. Then we can do some extra zeros. So do you want to see some numbers? When we might want to do this? Would that help? Maybe an example? Or questions? Everyone's quiet today.
I do have a question. Back to the not asking for you to give a difference between beta and beta binomial. But if it's extremely unlikely for you to get that 0 or 1, but it's still a possibility, should you use the beta binomial over the beta, because the beta is only for when you know you will never get a 0 and a 1?
I think that if you don't have zeros and ones, you have the choice of using beta binomial or beta binomial.
Okay.
I don't think you have to pick beta in that case.
Okay.
And I've also asked, so Walt Stroop was at Nebraska when I was there. He wrote a whole book on generalized multi-level modeling. And I read that book on vacation, sitting outside by the pool, as one does. And when I came back, I asked him, like, what if you have zeros and ones and you want to use beta? Like, what do you do? And he's like, oh, I just kind of move them in. I'm like, okay, you got a 0, now you're 0.01. You got a 1, you're 0.99. Problem solved. I'm like, oh, I could have done that. Apparently I am a statistician after all. Hooray. No, I think the reason that you would do beta is if you have some kind of like crazy bimodal something. Like that's when, because binomial can't anticipate that. Binomial is a one-hump distribution. So that's when I would turn to beta. And then you'd have to figure out what the heck you're getting back in terms of parameters. And that's,
How exciting.
yeah, that's non-trivial, is what I would say. That's non-trivial. All right, other questions? Want to see a picture? What do we think this outcome? This is performance on a test measuring grammatical understanding amongst, I believe, 4th graders, actually. How would you characterize this distribution? Negatively skewed. Yeah, negative is because that's which way the tail goes. Does it look like we have any floor or ceiling effects, maybe? Yeah, we got about 40-some% of the sample got 100%. So do you think like a general linear model would be appropriate for this? No. How about if this were a longitudinal study? Do you think a general version of a longitudinal model would be appropriate for this, given this looks like? Okay, hit me. Questioning.
So, and it goes back to, like, when you're using models, what matters is not the distribution of the outcome.
Correct.
It's the distribution of the residuals.
Yes.
So, when we're looking at this, if this is just our distribution of our outcomes, we can't automatically tell if we need a different distribution. We have to run the model first, and then we see, is the model that we ran more or less accurate at various points along the scale, right?
Yes, so let me repeat that to make sure the recording catches it. So the comment was first, we can't just stare at a distribution of the data and know what kind of model we need. That is accurate, because the assumptions are always about the leftover parts, the conditional part of it, not the original. However, I can't see a universe in which like this isn't going to be some kind of skewed with a very prominent boundary. Like the fact that I don't have the other half of this distribution makes it unlikely that any kind of symmetric distribution would be a reasonable choice. So I think you can look at these pictures to anticipate like what family you might need to head towards, but for sure not decide based on just a marginal picture like this. Okay, did I capture what you had said, or is there more to it? I think I'm forgetting a piece.
Well, I think I just still don't understand.
You don't understand?
Yeah.
That's fair. I don't either.
Yeah.
If I'm being real, like I don't understand all of this. I'm working my way there. But I'm asking for you to anticipate, just like, do you think if this was a longitudinal distribution that a general version of a longitudinal model would work if you had this kind of picture? I'd say probably not. But why I'm asking that is because this data set came from a longitudinal study. Look, it's me. I'm third. It's one of the first papers that I helped publish from some stuff I did with graduates in graduate school. This is Mabel Rice's data. I continue to work with her on papers to this day. She studies children who have specific language impairment. So they have issues with grammar that do not translate into other developmental delays or disabilities. For whatever reason, grammar is just hard for these kinds of kids. And she's interested in the genetic contributions, the environmental contributions, and then what happens to them? Like, do they eventually grow out of it, or do they end up with deficits? And the answer is they end up with deficits. So this was part of a longitudinal study examining grammatical tense deficits in children with speech, specific language impairment, and non-specific language impairment relationships with nonverbal IQ over time. And my job on this project was to do the growth modeling for these outcomes. And guess which kind I did? The wrong kind, the general kind. Can anyone guess why I did that? Vladimir, why did I do it that way? He knows the answer to this.
I think that because at that time you didn't know how to do it better.
That's right. 2004, Lisa did not know any better. That's the answer. I look back at most of my papers from like that era and I'm like, ugh, no, like that's not good. But it was the best I could do at the time. And quite frankly, if I couldn't look back and see growth, then I'm doing something wrong. Because to be a scientist, to be a scholar, means that you have to accept that you're never going to know everything because the field keeps moving on. And we just have to try to stay with it as best we can and keep learning new things. Part of that would have been what was possible in software in 2004. Like there's more choices for distributions and options in generalized models than there was back then. So yeah, I did the best that I could at the time. I did actually build a generalized longitudinal example with the same data, and all of our primary conclusions were the same even after we fit the right model. So
Interesting.
it didn't matter as much. But I picked the fourth grade occasion in this instead of the full range of longitudinal data because it was the most egregious in terms of not normal as a starting point. So by fourth grade, the children who do not have a specific language impairment are doing just fine on this test. The ones that have impairment, though, some of them are not doing well at all. So then the question would be like, what predicts that? What differentiates levels of impairment in children who have this condition? So I had my usual narrative about the packages I've chosen and why. This is going to be an example where we have two predictors and no interaction terms because the distribution part is hard enough. So what we're going to have is which group they're part of. That's going to be coded so that non-specific language impairment is 0 and specific language impairment is 1. So non-specific means they have general deficits that are past grammatical understanding. They extend to other areas. And the other thing we're putting in the model is mother's education. Because that is, I know, that is a covariate that reviewer 3 will yell at you if you do not put in the model in this world. You have to control for mother's education. What about father's education? It's fine. It's my fault if my kid doesn't understand grammar. It's not his dad's fault. But that is the world as it was at least in 2004. So, and I am centering that because we have 0 equals 12 years of education so that our reference mother would have a high school degree. Okay. So first things first, I need to figure out what my model is doing. So my research question for my empty model is, do I understand what's coming back? Because that's the logical starting point. So the mean for this variable is 0.92. Very high. So on average, if I were to convert this into a metric of 100 questions, the average person's getting 92 of them right. That creates an average accuracy rate, or a proportion that we're going to predict, of 0.92. So this is what my model needs to be giving me back, if I understand it, because we're predicting the mean of this variable just like usual. It ranges from a low of 0.35 up to a high of 1. So the very long tail here for folks who had some difficulty. So in terms of building the data, a few extra transformations relative to the typical part. I did not put the data in your download folder because it's real data and I don't have permission to share it. And for that reason, I went ahead and rather than importing it from Excel format, I did it in the dedicated Stata format. So if you have a data set in Stata already, you don't have to import it. You can just say use, and it's .dta is the extension. So in this data set, everything is in lowercase because that's what happens when you convert a data set into Stata from SAS. It defaults to that. So I have NLI v SLI, that's my group variable. I'm going to have mom ed centered at 12. And proportion correct is what was in the original data. So I didn't have the number of trials stored with it anymore. I just had the proportion. So accuracy is what I have as my DV. To use it in a binomial, I got to hack it back into events and trials. So here's how I did that. First off, making a new variable called number of trials, that's 100. I am then generating what the number of correct responses to my 100 trials would have been by multiplying the number of trials times proportion correct, and then rounding to the nearest integer. So this would create a new variable that is essentially like 92 out of 100 for a number of correct rather than 0.92 as the proportion. So you don't have to do this if you know how many trials you already had in the first place and how many you had correct, or how many events there were, is the language that people use for this. I had to reverse engineer that here because all I had was the proportion.
So here does trials mean people?
Trials means, you can think of it as test questions. Opportunities to get a 1. And because I had it out of a scale of 0 to 1, I just pretended I had 100 trials to turn it into a number correct as opposed to proportion correct. It's just a hack to make this work. And then, for reasons that will become clear later in the handout, I had to generate number incorrect and proportion incorrect. Let me go back to the picture and see if you can guess why. Do you remember what we were worried about in count data? Beyond over-dispersion? Bounded at 0 and too many zeros, right? 0 inflation. Do I have 0 inflation here? No.
The reverse.
I have 1 inflation, I would say. And it turns out I could not find a software routine for 1 inflation. So I was like, I can fix this. We're now modeling incorrect responses as the events. 0 inflation.
1 minus?
Yep. I can fix it. So halfway through this, I'm switching to incorrect responses so that I can examine 0 inflated models as reciprocal of this distribution. If anyone on the YouTube is listening and knows how to do 1 inflation, please send me that code. I'd really appreciate it. Hey, that has happened before. When I've asked the YouTube audience if they know how to do something, occasionally people will email me with the answer to my question. It's amazing. Question?
Do you have to round your answer to the nearest whole for this to work?
Yes.
Okay.
Because it's events as a discrete over trials as a discrete.
Understood.
Yep.
Just making.
Yep. So that's one, 92.1 versus 92. Yeah. You got to make some compromises here. Then I made some pictures in Stata as well. For the 0 inflated versions of these models, I had to find a package called zbin, 0 inflated binary. And to do the beta binomial distribution, I had to find a package called betabin. So if you uncomment these lines and run that, a little window will pop up, and then you can download the package. So it works the same as CRAN, essentially, from within Stata. R folks, I'm not going to forget you. I read in my SAS data set into R directly. I found a package that, I think it's called Haven is the package that does that, if I remember correctly. Yep, and so there's a function called read SAS, so I read in the SAS data set. Then I had to do the same things. So I'm building a new variable for number of trials, building number correct as the proportion times that number of trials, and then rounding it. Did the same thing for proportion incorrect to get the 0 inflated models. And then I made a picture of that as well in R. So they look a lot like that one.
Different question.
Different question, different answer, maybe.
Maybe. Chose 100 to make, just nice percentage. Could you, if you wanted to include more percentages, could you multiply by 1,000 or 1,000,000 or whatever you chose?
Yes, I tried that and it threw up.
Very good.
So I was like, that's not gonna work.
Okay.
Yeah, that's where I went first to try and keep the precision.
Yeah.
Yep, theoretically, yes.
In practicality, no.
So what's nice about this, n trials I generated as a constant here. It doesn't have to be. So this would be a column in your data set, like how long was the child observed for, or how many questions did they get? And then you have a column for how many incidents did you have, or how many accurate responses did you have, and they don't have to be the same across people. So it will generate effectively a proportion, even if there's different denominators, which I think is good. All right, so we got to figure out, first thing here, what are we modeling? Empty model. This should return our mean if we understand the parameterization. So the way this works is that we're eventually trying to predict the number of correct using a binomial distribution with a parameter p, which is going to be estimated. That's going to be the probability of any one trial being correct. N trials is the number of trials. That's in your data. That's not a parameter. That's something it needs to know. The empty model to predict p looks like this. The logit of the probability of a correct trial is just a mean, beta 0, one intercept. The conditional mean then, once I get the probability that any trial is correct, I multiply that by the number of trials. And then I get the expected number correct instead of proportion. And I have variance that goes with the mean as tied together like this. So in Stata first, and then we'll see R as usual. I'm back to GLM, which stands for Generalized Linear Models. Now note what's in the outcome here. Number correct is the outcome according to Stata. Question.
I have a question moving back.
Okay.
Instead of looking at Stata, just looking at what we're trying to do.
Okay.
This is difficult for me to get my brain around because, of course, you know, I do look at test data. And I know that the probability that any one item will be guessed correctly differs from the probability of other items being guessed correctly. I
Yes.
guess I don't understand what is the value in finding like the value on average of one item being guessed correctly and then multiplying that by all the others to get the mean. Because it seems rather that we should like, the mean should come from the various values of like all of the items rather than the other way around. Like we're losing information
Yes.
about our data if we do this way.
Okay, yes. So the question was, each individual item probably has a different probability of being correct, because some items are going to be more challenging than others. We are completely ignoring that and assuming that the trials, the items in this case, are equivalent, exchangeable. So yes, if you have items that are meaningfully different from each other in their difficulty or severity and in their discrimination, you would be ignoring all of that and doing this. You would want a different model in that case.
This, I don't think there's any test where you can really assume that all the items are equally, I mean, unless it's like,
Sure you can.
you know,
This is the kind of stuff that I did as a graduate student at Kansas in the world of cognition and attention. I can make you stare at a screen and tell me if the T is on the left, tilted on its right or its left, and I'll make you do that 100 times.
so
Mm-hmm.
it's like the same task.
It's the same task. Yep. Or if I draw, if I flip a coin, right? It's the same thing. So the trials are considered exchangeable in this case. If you want to have item differences in difficulty and discrimination, take the IRT class or the SEM class, and we'll talk about it then.
That's the original probability that we're working with P sub I, not based off of what we got for our count for like our 92 versus the over 100.
Yes, so what we're working with is we're predicting the logit of the probability that any one trial is a 1.
Mhm.
And then to get what the then implied mean of the variable would be, it's the number of trials times the probability. Yep. Yeah, it is tricky to understand, but it's a roundabout way of saying we're predicting proportions. Very roundabout. Okay, so let me make a point of telling you how the variables in the model work, because this I screwed up at first, and it took me a minute to realize why. In Stata, it wants the number correct here. So this would be like the 92, not the 0.92. So this is what I built out of number of trials times their actual accuracy score. Link equals logit, that one's self-explanatory. Then family binomial, and then n trials goes here, that's the denominator. So it wants to know how many events out of how many possible. So it's building the proportion inside the model for you. This is the numerator, this is the denominator. If you fit this same model in SAS Glimix, you literally input it as a fraction. Like you would input n correct divided by n trials as your DV. So you have to read the documentation to figure out where stuff goes, but this is where the pieces go. So this is why it's advantageous to have this as a variable, because then you can have different amounts for different people. If they had different exposures, essentially, to whatever you're asking them to do. So then it tells you variance function is binomial. In this case, the mean times 1 minus the mean, upweighted by the number of trials. The link function is the log of the odds of the probability of a 1, upweighted by the number of trials. Cool. So our 1 over degrees of freedom Pearson chi-square statistic is 21. Like, that's not good. So we know that this distribution isn't going to work, but we haven't even put predictors in yet. Our goal here is to figure out what the model is doing. That's our goal. Okay. So we get this back. The constant is 2.45. That's in logits. Now that's fairly high for a logit. What is neutral for logits?
Wait, yeah.
Is it 1 or 0?
Wait.
It's review time. Yeah, logits were like in January. We're in April now. No fooling. Okay, so probability of 50-50, like, right, 0.5 over 0.5 is a 1. That's odds. And if I take the log of the 1, that's my logit, and that's 0. So a probability of 50-50 corresponds to an odds of 1 corresponds to a logit of 0. The fact that this logit is very positive means that the overall mean is much closer to 1 than it is to 0. And in fact, here's my handy-dandy inverse link function. E to the logit over 1 plus e to the logit gives me this number. Does that look familiar? 0.92.
That's actually 19 1. It goes
I
all
know.
three places.
Yeah. So we got it back.
And that's good, right?
It is good. At the end of all of this, you are predicting the proportion. That's what you're doing. It's just this roundabout way of how many trials and da-da-da-da-da. See, this is comforting to me. Like the 0.92, I know what that means. That is the probability of getting a correct answer for any trial. And if I wanted to know then what the implied number correct is, I multiply that probability by the number of trials. And in fact, if you ask for Stata margins, that's what you get. It does the math for you. So the expected number correct, as it is put in the model here, is 92.12. But what the model is predicting is the probability of any one trial being correct as the 0.92. So if I had told it I have 5 trials, then it would take 0.92, multiply it by 5 to get this number here. Yeah, I'm not doing that math in my head. Don't do math in front of people if I can help it. So what we're predicting then is accuracy. On average, accuracy is 0.92. All right, with me so far? Our folks, ignore everything I just said, yours is different. Fun. So I'm saving the sample size minus the number of fixed effects to be used in computing Pearson chi-square over degree of freedom again. We are back to the VGLM function within the VGAM package. I'm going to be honest with you, I don't know what all of this means. I just followed the examples until I made it work.
I love it.
The documentation is horrific. It's completely unhelpful. So I just started typing in words, honestly, until I found what I was looking for. So data equals, I know that one. Got that part. Binomial FF.
Fantastic function.
Yeah, when I first saw that, I read binomial AF, and I'm pretty sure that's not what they meant. Not going to say that one out loud either. You can ask the internet what that means. So binomial FF, I think, means something function. Presumably there was already a binomial F somewhere else, and so they had to add an extra F. That's the only thing that would make sense. Link equals logit link, in quotes this time. Multiple responses equals false. I do know what that one means. It allows you the option to, instead of inputting a column of the number of events, to put in all the columns. Like all the 0, 1 columns stored like in wide data. And as opposed to adding them into one column. You can input it that way. I did not see that being helpful. Formula equals cbind. Yeah. And then number correct, we had that before, and number incorrect instead of number of trials. That's what it wants. So it figures out what the total is as the sum of these two things. So Stata wants number correct and number of trials. R wants number correct and number incorrect. And I figured that out through trial and error. Pun intended. So this means give me an empty model with only a fixed intercept. The same as having nothing after the comma here. No predictors yet.
Question.
Yes.
The way that looks is it looks like we're trying to have one predictor with two outcomes that it's working with. Is that kind of really what's doing?
No, it's using this information to build your proportion. Except it's doing it.
You're binding those
Yeah.
two together. Never mind. Sorry.
Yeah, no, it's just that it's not the in total. It's
Right.
in incorrect. So
Okay.
it's putting it together
yeah.
just differently.
I was
Yep.
just- yeah.
And fortunately, though, it agrees 2.45 whatever in logits corresponds to a probability of 0.9212. So we're back to where we started from. Name of linear predictor, logit link prob. Thank you. That's very helpful. Now we get this thing. We get a warning message that the Hawk-Donner effect was detected in the following estimates. And I'm like, what the heck is that? Are these people? Should I be concerned? Yes, these are people. Basically what it means is that I had trouble estimating the intercept because it's pretty close to the boundary. So I found some information about it. You can read about it here if you're interested. But that is a warning message that shows up throughout this example. I don't think there's anything that can be done about it. I think it's just warning you that you're getting close to the boundary. But I can figure out what the implied proportion is from that logit. It's e to the logit over 1 plus e to the logit. The shorter version of the formula is here. 1 over 1 plus e to the not logit, minus 1 in here instead. And then Pearson chi-square, we're getting it the same way as before. The only difference is in terms of the degrees of freedom. It's 21, so way too high. So the distribution doesn't fit yet, but we know what the model's predicting, so yay for us. Okay, questions or comments?
I have a question going back to why can we look at a distribution of the outcome and suspect that the residuals will also be wrong? I'm trying to figure out in my head, and I'm thinking it's because we presume that ability to get the question right is related to some kind of latent factor variable. And we assume that at higher levels of ability, students will get more items right. And at lower levels of ability, they may not get it right. But we presume, like, maybe we got the ceiling effect because the items that we chose were not difficult enough. And if we had asked for difficult items, we might have seen more of a normal distribution of responses. But as it was, they kind of like walled up here. So like here, we have kind of a group of people, including those who really do have super high levels of ability, also maybe some students who have intermediate levels of ability.
Mhm.
So then if we use a predictor to try to see if that latent variable can predict scores, it's like accurate, more accurate at the lower ends of the model, but then when we get to the highest end, we've got that, like we just bumped it up, and it's not accurately discriminating between people with intermediate and high ability on that variable. And so it's less predictive for the higher, like by the ceiling. Is that true? Am I making this up? I'm going crazy.
You're not going crazy, but you are, I think, talking about a different context of items and whatnot. So these items, again, they're not like trials, they're exchangeable.
Okay.
So we're not even monitoring differences in difficulty and discrimination in those things. But you're right in that, like, this distribution, let me go back to the picture here. Since I don't know if we have the strength for one more model, but we have the strength to look at a picture, right? We can look at pictures all day long. This is a SAS picture, you can tell from the light blue. This distribution could be a consequence of having items that are too easy.
Like all the items.
Yeah, like this is the same. Her items do have differences, but they're all built the same way in terms of this particular task. They're meant to be exchangeable. So we don't know if this distribution would change if we added harder items that would spread out the people who look like they're super high ability. But that's much more of a measurement question in terms of how we would maximize the distribution and measure individual differences accurately. We just got to dance with who brung ya, as we would say in my Midwestern vernacular. Like, this is what we're stuck with. But if that is the case, then if you were to introduce harder items, you would expect to see the pile of ones spread itself back out again, and then you would have differentiation of the higher abilities. But there's no latent variables in this model per se. There's no latent ability. This is not an IRT model. However, IRT models are generalized models. So, yeah. IRT is factor analysis on logits and probits. That's what it is. And that's the way I teach it. So, in the same way that you would start with linear regression and do logistic regression, you can start with confirmatory factor analysis and then do item response theory. And then you can rearrange them into something that looks a lot more similar across the two. So that, I think, is where you're going in your head, is sort of like the testing practice that you're used to in terms of your work and measuring people's language abilities. Like, this is more of just like an experimental task where the trials are thought to be exchangeable for better or worse, and this is the distribution that we ended up with. And I believe it's because the same items were given in the original study starting from kindergarten up to 4th grade. So if I looked at this distribution at kindergarten, I might see more of a zero inflated pile because they can't do it yet. And as they age, the pile kind of moves over to the one side.
But then would the latent variable be age?
The latent variable would not be age, but it would be correlated with age in the sense that as kids get older, they get better at this, hopefully because of schooling, also because they pick up reading and they see more examples of grammar and action and that kind of thing. So, question? No, just stretching? Okay, yes. Well, for those of you who are parents, I can tell you that your grammar takes a big hit when you become a parent, because you used to answering questions like, I need carry you. That's because I would ask my son, do you want me to carry you? And then he'd later, I need carry you. That makes perfect sense to me. One time he said, Mommy, why you are talking? What you are talking? He meant, what are you talking about? Mm-hmm. But then we start saying things like that to each other. Why you are doing this? And then it sounds completely fine. So my grammar got all screwed up by toddlers, just now getting back to where it was going to be. So, yeah, there's a lot to this, and I'm happy to sort of talk to you about the connections of these things. But in those types of item models, we're not predicting the total. We're predicting each item response individually from characteristics of the item and characteristics of the person. This is analogous to predicting a sum score, disregarding all of the item differences. Different animal.
It's hard for me to understand this because I can't think of like a context where I would want to know this.
The context is modeling proportions. I think that's the context. It's like if you think of the trials as exchangeable and you want to know how well someone did overall, then this is an approach that can give you that information. We'll keep trying. All right, Vladimir, you want to help?
Yes, I have two questions besides.
Oh,
First,
questions. Uh-oh.
Yes, if we are working with sum scores, we must transform those sum scores into proportions to be included in the model, right?
No, you would start with the sum score, start with the number possible, and then the model builds a proportion. Like I started with some proportions in the data, so I had to reverse engineer sum scores to be able to put them in the model.
Awesome. Now, about the interpretation of the results, because given that now we have a sum score, what the model would be predicting is the proportion, the probability of getting 1
Mhm.
in any trial.
That's what it is, probability of
does-
any one trial.
But it doesn't make any sense for a sum score, I think, because for a sum score, let's say that we have 4 items between 1 and 4. So floor is 4, ceiling is 20. 16, sorry. But this idea of 1 doesn't make sense, right? Because
Yeah, if it's ordinal data, then this wouldn't work, because it's not, the possibility isn't 0 or 1 for each trial.
Exactly. Okay.
Yeah, but you could hack a scale score into a 0 and 1 metric to use this if you had scale scores that had upper and lower boundaries, that were ceiling and flex. Yep.
Can we treat that sum score like a latent score, so we can say that a smaller score means less, how to say, you don't have the attribute too much. A higher sum score would be you have more of the attribute.
Yes, but if you're in some score land, you don't know if your sample is smart or your items are easy or both. They're tied together, and that's the problem.
Yeah.
So, all right, we're into the
Oh,
next
we're-
class at this point, so.
Yeah,
Yeah.
and
And we're at
time.
3:15, so, thanks for being here, folks. I will hang out for a minute if anyone wants to ask questions. Otherwise, you can be working on homework 3 and let us know if you need help, okay? All right, cool. Hope to see everyone Thursday. Bye, Zoomers. Awfully quiet today.